So looking at number 7 on your notes, this is where we left off the other day. It says, find the function that is finally graphed after each of the following transformations is applied to the graph of y equals x squared in the order stated, and then graph it on the grid. So I start with the parent y equals x squared. Good? Yes? Okay. And then I'm going to shift up 2 units. Okay, I'm going to shift up 2 units. So I was here, and I'm going to go here, right? I'm shifting up 2 units. I'm doing like a rough sketch to keep track. Everybody's okay? Yes? And then it says shift right 3 units. So from there, I'm going to go right 3 units. So what's my vertex right now? 3, 2. Yep. If we're just kind of keeping track of where we're at. Everybody good so far? Yes? Then it says, reflect about the x-axis. Where would that go if I reflect that thing about the x-axis? So 3, -2 would reflect about the, yes, reflect about the x-axis. I was doing the next thing. Jeez, that's embarrassing. So I'd be down here at 3, -2 when we reflect about the x-axis. Are we okay? Yes, we're good? Okay. Then it says to reflect about the y-axis, which is what I was trying to do next. Where do we end up if we reflect about the y-axis? -3, -2. So we're over here. Everybody okay? All right. So now that we've sort of visually sketched that out, let's think about what that equation would have to be, right? What would be our y of x? Y equals. What would be my a value? What makes it be upside down? A negative, right? So it would be negative. Okay. There's a horizontal translation, so there's going to be something in parentheses, yes? If we end up here, what's going to be in parentheses? Yep, so I'm going to have x plus 3, right? That thing's going to be squared. What's going to be outside the parentheses? -2, because it ends up down. So if I now graph this, I'm going to put my axes in the middle because I don't know where's the best place for them, so I'm going to assume middle. Haven't done this problem since last year. Don't happen to remember this one exactly. All right, so I am at -3, -2, and I open down. Remember our little table of values that we used. If you do 0, 1, 2, 3, and you square them, right, you get 0, 1, 4, 9. That's like the parent function. So from here, I can go out 1, down 1, out 1, down 1 to both sides. And then I can go back to the vertex and go out 2, down 4 to each side, and that gives my parabola. For right now, I'm just going to label the -3, -2 at the vertex, because this is more about seeing the importance of order than it is about making a fancy graph. Are we okay so far? Yes, we're good? All right. So I'm just going to switch colors so that we can tell the two of them apart really clearly. But I'm going to take the same method that I did before, where we're going to just kind of like draw a little visual sketch to think about what's happening. So this says start with your parent and then reflect about the y-axis. Well, what happens to a parabola if I start by reflecting it about the y-axis? It doesn't turn. Here's my y-axis. I reflect over my y-axis. It's the same. You can't even tell, right? Because that's reflecting this way. Are we okay? So this, it's like I didn't even do it. Are we okay? If something is symmetrical to the y-axis and then you reflect across the y-axis, nobody can tell. Okay? All right. Then it says shift up 2 units. We've done that before. It's going to come up here. Then it says reflect about the x-axis. Will we be able to tell that that one happened? We will, definitely. Because not only will it be upside down, but it'll be 2 units below instead of 2 units above. We okay? All right. Then shift right 3 units. So we're over here. Does that make sense? Yeah? Okay. So what's going to be the vertex for this parabola? 3, -2. But it's otherwise the same shape, right? So I can do my over 1, down 1 thing, and then go back to the vertex and go over 2, down 4. So now my vertex is at 3, -2. So that's kind of interesting because we did exactly the same 4 transformations. But because we switched up the order, we ended up with a different graph. So clearly order matters in the way that we go about doing these things. I can't just do it in any order I want to. I won't always get the same picture. Now let's think about what that equation would be. So my other equation, the one for the blue one, was y equals negative x plus 3 in parentheses squared minus 2. What would be this equation? Y equals negative, in parentheses, what am I going to have? X minus 3 squared, still minus 2. So the only thing that ended up changing in the equation is a plus 3 changed to a minus 3. Are we good? Yeah? All right, flipping the page. We're going to do some stuff that's a little bit different. This is getting a little bit more into the like what a lot of schools would consider the pre-calculus way of thinking about transformations. Oh, and quick reminder, let's see. Oh no, I see you every day, so I can remind you again tomorrow. But what's due Friday morning? The ed puzzles, because we're going to do lesson 6, I think, on Friday. Am I right about that? Is that due Friday? Yeah? It's either Friday or Monday. I can't remember anymore. Monday. Is it Monday now? Oh, okay. So it must be due Monday morning? Yeah. All right. Okay, so just remember we want to get those ed puzzles done. Okay, if 3, 6 is a point on the graph of y equals f of x. Okay, so I just have this generic thing, y equals f of x. I don't know what that function is, right? I don't have an equation for it. But I know that this point is on it. Are we okay with that? All right. Which of the following points must be on the graph of y equals f of negative x? Okay. So instead of being f of x, it's f of negative x. So the x's are being replaced with their opposites. So what point do you know must be on there? Negative 3, 6. Does that make sense? This is like a hint at how the SATs ask you these types of questions. Okay, they're asking you to think more generically than just understanding a particular function and maybe being able to do something with the graphing calculator to get around your understanding. Okay, all right, number 9. If the point 1, 3 is on the graph of y equals f of x, so some function called f of x, we don't know what that function does, but it says the point 1, 3 is definitely on that function. Which of the following points must be on the graph of y equals 2 f of x? So 2f of x is what sort of transformation? Vertical stretch, right? Because it's being applied to the output. Okay, so of the points that they gave you, which one must be a point on that graph? Vertical stretch, C, because it's affecting the output, right? If I stretch something vertically, my x's don't change, but my y's do. My y's are going to be twice as tall as they would have been otherwise. So the 1's going to stay the same. The 3 is going to double to become 6. Are we okay? All right, let's keep going. Sometimes they like to give you wackadoodle looking functions and ask you questions about them or ask you to redraw them. It says the graph of a function f is illustrated. Use the graph of f as the first step towards graphing each of the functions below. In each case, state the type of transformation that is applied. I will tell you, if you state the transformation first, way easier to make the graph because then you just visually can move the graph, okay? So if capital F of x is equal to f of x, that thing given, plus 3, what transformation is being applied? Vertical translation, okay? So this is vertical translation up 3, right? So I can sort of think about moving each of those individual points and then play connect the dots to draw the new function. So when I do that, if I'm moving my graph up, I'm probably going to move my axis down. Does that make sense? All right. So axis down to give myself more space. I don't need to change where the y-axis is. That can still be basically at the middle. So the point -4, -2, if it moves up 3 spaces, will be where? -4, 1. The point 0, 2, if it moves up 3 spaces, will be where? 0, 5. The 0.22 will be 2.5. And the 0.40 will be 4.3. Now, because the scale in the image that was given to me is different than my scale, it looks like I changed that graph a lot, but it's just a scale issue. Is everybody okay with that? Yeah? All right, now, I probably would very specifically label these points. Oops, I did that one wrong. It should be 4.3. 4.3. That's better. 4.3, 2.5, 0.5, and negative 4.1. All right, so let's look at the next one. Capital G of x is going to be f of x plus 2. What transformation is that? Horizontal translation. Is everybody okay with that? Yes, we're good? All right. Oh, I have to remember how your book does this. All right, so when we have f of x plus 2, this is going to be a horizontal translation, left 2. So every point on that graph is going to be 2 spaces to the left of where it was before. Does that make sense? Do you need me to walk you through each point, or can you just do that and then we'll compare? We're good? We'll do it and then compare? Okay. All right, so when you're ready to compare, go ahead and look up. So we can see that each of the coordinates just has an x coordinate that went 2 spaces to the left of where it was before, but everything's at the same height that it was before, and the shape of the graph is the same as it was before. We're good? Yes? Okay. So looking at C, again, we're comparing to the same original parent function, but now this is f of 2x. So that's not a vertical translation by a factor of 2. What is it? It's a horizontal compression, right? This is going to squish it in. And it's going to be like multiplying everything by a half, right? So that's going to take all of our x values and take half of each x value. Okay, so this takes half of each x value because it's a horizontal compression. So you can take a minute, you can draw those new points, and then look up when you're ready to compare. So this one's kind of interesting because one of the points doesn't move. Because half of 0, still 0. So when you have a horizontal compression, remember you're compressing towards the y-axis. So anything on the y-axis won't go anywhere. Just like with a vertical compression, you're compressing towards the x-axis. So anything on the x-axis won't go anywhere. So this one actually sort of gives us a different shape. The same directions, but it's squished. Questions? We're okay? All right. Is that the end?